Yeah, where's Tristan? Come on, man, more people to worry about. Okay, let's do one that's kind of a little more intricate. And again, chromium and iodine are always classic ones for these things. Let's do I minus plus Cr2O7, a little dichromate. This time, instead of chromium going to chromate, we're going to take the chromate back to chromium. And we're going to make iodate instead of triiodide. So variants on a theme here with some classic guys. So let's see, the first thing we have to do, ooh, I should have put that in black. First thing we have to do is break it apart into its constituent groups here. So let's break it apart into the I minus, going into the iodate, and the dichromate going into the chromium 3 plus. Does anyone want to take a stab at it, or do you just want me to balance it? Hearing none, I'll say Gherkin. Can you do the top one for me? Oh, you guys thought you'd get away with it that easily.
Wait, what did you say?
I want you to balance the iodate here. I want you to balance that first equation for me.
Okay. Well, there's the same amount of the I's on each side.
Check.
And then you can add 3 H2Os to the left to balance the O's.
And I think we've been doing that in red. Okay.
And then add 2 H pluses to the right. Oh, sorry, 6.
Yeah. No, and this is why we do this, right? You know, whether we're going too fast or we miss something, I know exactly why you said 2. But remember, there's 3 times the 2 in the water, so we need 6 on there.
Yeah.
Now what do we need?
Let's see. Sorry, I missed the lecture.
Oh, that's right. That's right. After saying, "Hey, are you okay?" because I missed you, I'm putting someone who wasn't here on the spot about that. I'm sorry about that.
No, it's okay.
She's like, "I got this." So what's the charge on the left? Because the last thing we have is the charge.
Oh, yeah, the charges. The charge on the left is a -1.
And what's it on the right?
It's a +5.
So how do we make -1 equal -1?
You add 4 electrons or 6. Oh yeah.
Now, and I'm actually glad you're making these subtle and small mistakes, because this is how it goes. You know, especially when it comes down to the electrons. I said it last time. The electrons is always the one that trips people up, because it's almost like we have to think backward. I don't know what it is, but sometimes it just feels like, oh, I just need to add 4. Oh wait, no, 6. Wait. And so just be very cognitive that you have to be very careful by the time you get down to the electrons. That's the place that trips people up the most.
Yeah, okay.
Alexia, can you do the chromium for me?
Oh, okay.
Yeah, I wasn't here last lecture, but I still can do it.
Are you going to still try it?
Yeah.
Okay, go with your bad self.
So add 2 chromiums on the right, and then 7 H2Os on the right also. And then add a electron on the right too.
Got your H pluses.
Oh, and then,
right.
Yeah.
So now we got the 7 waters and the 14 H pluses. Now let's take a look. What's the charge on the left?
12 plus.
And on the right?
It's 6 plus.
So
you'll do so 6 minus on the left.
that is correct. 6 electrons on the left. Nicely done. So that means when we get down to it, those electrons would end up canceling out, and we would end up with, oh, and look what cancels out. 6 H's there, makes it down to 8 there. And 3 of those waters goes away to give me 4 waters. So this one I like because it's not just a matter of the electrons going, but in the balancing of them, we are going to have to take into account some of those other quantities. So at the end of the day, we end up with 8 H pluses plus a Cr2O7 2 minus plus an iodine goes to make an iodate plus 2 chromium 3 pluses plus 4 waters. Now, just so we have it here, I went ahead and looked these up. The E naught for this guy is negative 1.085 volts. And the E naught for the second one is positive 1.232. So that means that if we just go ahead and add those up, and because they were 6 and 6 and 6 for the electrons transferred, we can just add them up. We don't have to worry about the N1, E1 stuff. We would get a positive 0.147, which means it's spontaneous, as written. Okay, so let's build it. Okay, one last thing that to do before we build it. The one on the top, is it oxidation or reduction? Contreras, you're at the top of my list on accident. All right, hearing nothing.
Is it oxidation?
It is oxidation because we spit it off. So this is our oxidation, which means the other one, which is usually the easier one because it's on the reactant side, we are gaining those electrons, so we are gaining is reduction. All right, so let's go ahead and build it. So I'm gonna make myself an electrochemical cell here. I'm going to go ahead and put the iodine on the left. So the iodine was the oxidation one. Ooh, I think I was putting oxidation in what, blue or green, or do you guys remember?
Oxidation in green and then reduction in red.
Thank you. I want to just keep it consistent since I was semi keeping it color coordinated. So in the oxidation, what were the pieces that we needed? It looks like we need some I minuses, some iodates, and some H pluses. So we need I minuses, IO3 minuses, and H pluses.
Do we need like the 3 H2Os too?
Well, it's in water already, right? These are aqueous already. So the water is always just essentially there. It's implied.
Okay.
So you could say we need water and then just, yeah, but it's already there. So on the reduction side, it looks like we need a Cr2O7 and a Cr3 plus. And looks like we also need some H pluses. Okay, so what's going to be our electrode on the oxidation side?
Platinum or carbon?
There you go. Right, you don't have the metal. What's going to be our electrode on the reduction side?
Chromium?
We don't have chromium metal. We have chromium 3 plus and dichromate, but not chromium metal. And so this is one of those strange ones where, man, we don't have any of it. So our electrodes will be either that platinum or the carbon, because we don't actually have the metal present. All right, so go ahead. That was just somebody coming there. Let's go with Rio. I haven't heard you in a long time. How might I get I minuses into solution? Give me something soluble. Or have a stare off with me. Or wait, was that something in chat flashing all of a sudden? Do we need sulfates again?
Sulfates again.
Sulfates won't get the I minuses. Remember, oh, that's fine. That's fine, Rio. Thanks for letting me know. Her mic isn't working. Since these are all the negative stuff, we would not be using sulfates to try to get more negative stuff in. I would go back to the good old, say, 1 molar, say, potassium iodide or sodium iodide. We can do the same thing with the iodate. The sodiums and potassiums, I just chose potassium this time just to switch it up from sodiums. But those, you know, sodium, potassium, those guys will always swim, so they'll always get the negative thing floating around. And then Dallas, how would we get H pluses in there? Thinking too hard. HCl.
Yeah, that's the one. Sorry, I couldn't remember salt.
Whoa. So when we're doing these, you know, the one thing you want to keep in mind are your standard workhorses for getting things into solutions. You know, sodiums, potassiums, those will get you into solution pretty well. And of course, H pluses, if you can get away with it, HCl is a great one. You could use H2SO4, but the problem is that has 2 H's in it, so you have to be very careful about the molarity you chose for that. Using monoproducts is going to be a better way. So on the other side, thinking about trying to get things into solution, dichromate, we could probably do a 1 molar K2 Cr2O7. You could use sodium. What about the chromium 3? Let's see, Boudica. What would get chromium to get into solution? Or Chef or Mang. Is Mang here? I'll have to check up on, oh, here she is. Or Loban, or anybody?
CL3.
Yep, chlorides, right? Any of those halogens, well, except for fluorine. So I know all of you guys are getting like, oh, wait, you know, just start thinking about your solubility stuff and shout something out. You're not gonna be wrong unless you're wrong, and then I'll still just correct you and we'll be fine. But you want to start thinking about the things that you can do. We need H pluses. So what do you think? Good old HCl, I think will do it. Let's let them see each other. Which way are the electrons going?
Nowhere?
Oh, no, they are.
The right. To right.
They're going to the right, which means who's going to the left? What's the counter ion?
CO.
Yeah, the CO minus or the dichromate, any of them. You could pick any of those negatives to go back across. That is absolutely right. All right, which one is the anode? Which one is a cathode?
The one on the left is an anode.
Right,
The one on the right's an, yeah, cathode.
because cathode, positive, reduction. So that's the way I always try to remember is once I realize which one is the reduced side, I remember a little CPR to jumpstart my career there. There we go. We just built an electrochemical cell. We could go in there and we could put this on and get that voltage. Now this is one of the more complex ones to try to do because there's so many parts in there. But if you can wrap your head around this, you can do any of them. Do we have questions about any of that?
Question.
Yes.
So when you are element or whatever, you just have to make sure that they're balanced. So like you put the CrCl3 to balance out the 3 plus in it?
Yes, yes.
Okay.
So you need the 3 chlorines to get that chromium 3 plus into solution. Yes.
Could you use something else like phosphate? Or is that not soluble? I don't know.
No, yeah, you are correct. Chromium phosphate would be insoluble. Typically the ones that are used the most, sulfate is used a lot. The chlorides, as long as you're not dealing with silver, mercury, or lead, you're good there. And of course, sodium and potassium to get any of the negative things into solution is a perfect way. And HCl is a classic to get your 1 H for every 1 molar solution type thing. You don't have to do like a half molar H2SO4 to make sure you only have 1 molar worth of H pluses.
Mm-hmm.
So, basically it's sort of to keep it simple. I decided to go ahead and make it a slightly more complex because of potassium. And I did the potassium because potassium iodide and potassium dichromate are actually very common chemicals in stockrooms. They don't usually come in the sodium versions of them. You can, but people usually use the potassium versions of them. And so that's why I did that. That's experience a little bit.
Okay.
So.
What was the whole thing with the, since we don't have metals in solutions, we use platinum or carbon?
Because if you do have a metal, were you able to watch last time's video?
No. Didn't
Okay.
get the chance.
It'll make sense if you go back and watch the previous one. But if you had a situation where the metal was part of the redox reaction, you would actually just use that as the electrode itself. Here, there is no physical metal. So we use platinum or carbon because they're very inert and will not participate in the reaction.
All right.
Okay. So why make all of these 1 molar? Why am I making them 1 molar?
So that they're equal to one another in similarity.
I keep coming back to this guy, standard state. All of those E naughts and everything we've been doing, they've been standard state conditions. So why standard state? Because let's face it, you can't always get everything to 1 molar. And so a lot of times, if they can't, they'll still get as close as they can, and then they'll do a little fudge factor later on to do what we are about to do. Okay, so why standard state? Because it allows us to do something really cool. All right, delta G equals delta G naught plus RT ln Q. Okay. Delta G equals negative NFE. Substitute that bad boy in. So we get negative NFE equals negative NFE naught plus RT ln Q. Divide by negative NF. Ooh, just gonna fall out here. What do we get? We get E equals E naught minus now, because of the negative, RT over NF ln Q. If we put some numbers in there, E equals E naught minus 8.314 joules per mole Kelvin. Standard state, 298 Kelvin. Number of moles N times Faraday's constant of 96486 joules per moles of electrons. We'll see that all those units right there will end up canceling. We'll have the moles cancel, but we'll keep the electrons, but on the bottom, but we'll have we'll keep these, well, I'll just do it with a pen. We'll notice that the joules go away, the moles go away, and the kelvins go away, and we're left with electrons and electrons. And then you can either leave it as a natural log or you can convert it. I'm going to go ahead and convert it because this is the one that I use. 2.303 log of Q. So this right here is just converting ln to log. And at the end of the day, you end up with this. E equals E naught minus 0.59, and it's either 1 or 2. Let me just punch it real quick. So I get to go off of memory on this one. I got 591. Over N log of Q. Okay. So we start with the Gibbs. We convert that all to voltages. And what we see is a way to equate whatever voltage you're at now by comparing it to the standard state. So this is comparing voltages to standard state voltages. Now here's the fun part. If we build all of our cells at 1 molar concentration, then that means that the concentration of our products over the concentration of our reactants, which is that Q, is equal to 1, and log of 1 equals 0.
Hey, Forrest, I think you're, it's 0.0591.
Oh, well, oh, yes. Oh, yes. Sorry. Thank you. I forgot a 0. Wow. Thank you. So, yeah, I can scroll up. Yeah. I know I probably went a little faster, guys. I apologize. I got all antsy in my pantsy about this one because what we're about to do is something really cool.
Up a little more?
Oh, up a little more. Oh.
Yeah, that big.
Wow, I went real fast. I went real fast. Sorry. So, so here's what we did. We have decided to start defining all of our stuff with 1 molar conditions for everything, and that was to basically make conditions where we are at standard conditions. And in reality, you don't always get to do that. So what I did do is derive the equation of what would happen if you're not at standard conditions. What if you aren't at 1 molar everything? Well, that's that purple equation there at the bottom. And it's just a way to figure out how far away from standard conditions are you, and what will that do to your voltage, okay? Now, having done that, and really all it is just, it's just math, and it's just converting some stuff and lumping everything down into a nice little constant. By doing all of that, what we end up doing is getting this relationship, but by keeping everything at 1 molar. So regardless of which side you're on or what's going on, you have one molar worth of your stuff on the product and reactant side. If you start there, then that log of Q, how far away you are from your equilibrium position, if you start there, your log of 1 equals 0. That whole right half of this equation drops out, and the voltage you decide to measure will actually be the standard state voltage. Now, of course, what's going to happen? You are going to put this all together, and you're going to start reading the voltage. And had we actually been able to do the experiment, you would notice that as you did the experiments, as you made your 1 molar solutions and you hooked up your voltmeter and you made the reaction go, the voltage would start dropping. Why would the voltage start dropping?
Because the reaction is happening, which alters the amount of ions in either side, and then you no longer are at 1 molar.
That is correct. That is correct. You have made this thing start to do what it wants to do, which means those ions are flowing. In the beginning, when we talked about this, Kimchi was like, wait, so those coppers just run up and they just sit there on the copper thing? And I said, yeah. And we talked about the car battery and how Ben said it looked all, pitted and bumpy and stuff. And that is the consuming of your reactants and or, making more product. It will start to make this thing not have the voltage that you want. Try it sometime. I've had to do it a lot lately as I've been cleaning the house. I've run across old batteries. And I'm like, okay, are they good or not? And I hook them up to a voltmeter. Now, nominally, your 1.5 volt batteries will measure somewhere around 1.5. If they are starting to go, you might see that it's only down to 1.4. By the time it gets down to 1.3, most of your devices will consider that battery to be dead. And you'll go like, oh wait, I still have 1.3 volts of stuff left. And your device says, yes, but I'm designed to run on something above 1.3. So as far as I'm concerned, there's not enough power. But you can actually watch your battery as you keep using it and using it. The actual physical voltage will drop. It's not like this battery's just going full bore, then boom, it just dies. It is slowly tapering off. And you can run across super old batteries, and we'll talk about it when we get to the battery portion. You can run across super old batteries that are truly dead, and we'll talk about how that happens, where there is zero voltage, not even a little, just zero. Okay.
So,
Go ahead.
what's the 2.303 conversion between natural log and base 10 log?
That's how you convert between the two. That's just the mathematical conversion for it. So now, full circle. I'm just going to go ahead and do it to just blow your mind. All right, here we go. I'm going to look at this. Silver chloride. Breaking up into silvers and chlorides. Now, what I'm about to show you is what is called the silver chloride cell or electrode, silver chloride electrode. It is also one of the standard electrodes. We showed you the standard hydrogen electrode last time. This silver chloride is also a standard electrode. It's used as essentially a benchmark for a lot of electrochemical cells, where comparing it to some sort of bubbling hydrogen apparatus is completely impractical. What they do is they compare the silver chloride to a standard hydrogen electrode and then use that scaling factor to determine the true voltage. But this is how it gets really fun. So the silver chloride electrode goes as follows. You can have silver breaking apart into silver ions plus an electron. This is the oxidation. Now, it may seem like, well, how are we breaking this up into an oxidation and reduction? I'm going to show you what they are, because unlike the other equations where you can clearly see, oh, it's chromium to chromium and iodine to iodine, there is no like, oh, there's silver to silver and chloride to chloride. We have essentially three things going on. And so I'm going to show you the two parts that make the whole of this reaction. Now, that electron is going to get pumped into the solid to break out solid silver and the chloride. These are the two ways of doing it. So what happens here? At the end of the day, if we add these up, you can see the electrons would cancel out here and the solid silvers would cancel out to give us our original equation of AgCl makes Ag pluses and Cl minuses. That's the overall. We got it back. Now, if we were to build this, we're going to have our oxidation. I'm just going to go ahead and put it on the left. I'll put our reduction on the right. Let's go ahead and build this guy. I'll go back up to those equations in just a second. I just want to put this here as a benchmark, guys. So I will be scrolling back up for you. Okay. So just so I pointed out, I keep calling this the silver chloride electrode. That's because we have the silver chloride electrode. That's how it gets its name. Now, in these types of electrodes, you will actually take a physical solid and force it to break apart by pumping electrons into it. And to do that, they're going to have to come from the original metal in question. So if we look at the oxidation side, we're going to need ourselves, some silver and some silver ions. On the reduction side, we're going to need some silver, some chloride, and some silver chloride. Okay. So, everyone's with me still, yes?
Yes.
All right. What am I going to use as my electrode on the left?
Solid
Silver?
Yep, absolutely. Solid silver. What should I use on the right?
silver.
Silver again, right? We see the metal, we use the metal. Okay. And this is the tricky part. How am I going to get silver ions into solution? Celeste. I like how everyone hides behind the anonymity of like, oh, yeah, my mic doesn't work, or I just stepped away, or, all right, Isa, jump in there.
Nitrate.
Yeah, we have to do the nitrate this time. This is where, like I said, hey, avoid it at all costs, except this is a noble metal. The only way to get it in there is to use silver nitrate. Okay, on the reduction side, we already have silver. Huh?
Bond with other things that are dissolvable.
What did you just like sheepishly say again?
Wait, does silver not bond with other things that are soluble?
Yes, it does, but not nitrate. So like we couldn't use silver chloride. We couldn't use silver sulfate. Those are precipitates. Silver, mercury, and lead. Those are the guys that don't like to play ball with other people. Nitrate's pretty much the only way of getting it in there. There are a couple others, but you can always be safe with nitrate. Okay, on the other side, while it may not be intuitive, I'm going to go ahead and do 1 molar HCl to get the chloride into solution. Now, the next trick here, though, is the AgCl. So how does that work? There's 2 ways to get the silver chloride into solution. The first is you just drop some in there. So you could just drop some AgCl in the bottom. It just has to be in there for this to work. The other way, though, the more common way, is to actually electrodeposit the silver chloride onto your solution, something called bearding. Now it's called bearding because under the microscope, it looks like the solid will have grown a beard, as it were, of this solid when you electroplate it. So how does that happen? What you would do is you would put that silver electrode into your acid solution. And then you just pump a little positive electrode or positive voltage on it. The positive voltage would see the chlorides race up to it, bind with the silver, and boom, it is there. And you only have to do it for a fraction of a second. You just need some of it there to start this reaction. And so they just drop the silver in there, put a positive, like zap, boom, the chlorides go boom, stick to it. Now you have AgCl on your electrode. So whether you drop it in the bottom or beard it onto the electrode, and bearding is the more common way of doing it, you would have all of your components.
So how do you make sure that you end up with 1 molar of the AgCl?
Well, by the time you go zap, beard, done, you've used all of like basically nothing of your HCl. You get bogged down in these little details, Dallas. Your molarity goes from 1 to 0.99999997, which is 1.
No, but don't you also want 1 molar AgCl?
How do you get a molarity of a solid, Dallas?
Point taken.
Right? And I'm not trying to make you feel bad. I'm trying to remind you of all these things because you know, in the moment you go, wait, we need 1 molar AgCl. Oh, no, we don't. No, it's a solid, right? What's the concentration of a solid, right? So, you know, as we do this, it's all these little details that we just have to keep floating around in our mind, and it works out, right? So, again, we take that HCl, we put our silver in there, we go zap, boom, it's bearded, we stop it, we leave it alone, then we hook up our battery and say, okay, go. And this electrochemical cell does that. The silver will throw its electrons over there, which means silver ions are popping off. And the chlorides will will do their thing on the other side as well. These electrons get pumped into the silver electrode, and all of this AgCl, this bearding, the chlorides come off of it. So the chlorides come off of that, and the silver is left behind as a lumpy mess on top of that red silver electrode. And this will continue to do it until you run out of stuff. Oh, and of course, our counter ion will try to balance that out. Whew. So here we have the silver chloride electrode. I guess I should note that. This is called the silver chloride electrode, often written as Ag/AgCl. Okay, so once again, as we look at this, we want to look at silver chloride breaking apart into silver and chloride ions. To do that, an electron has to be pumped into the solid to break it apart. And then you'd have an oxidation of the metal to balance that out on the other side. So what does this look like? We have Ag plus an electron making solid silver. The E naught of this guy is positive 0.7996 volts. Yeah, we know this one pretty darn good, guys. That's the reason why it is used. We have AgCl plus an electron, goes to make solid silver. plus a chloride. The E naught of this is positive 0.22233 volts. We know these very well. So if I were to figure out the voltage that I would see in this situation, hopefully you realize that I have to flip around the top one. All right, we're going to have to flip this one. And so I would have my silver breaking apart into Ag pluses plus an electron. That E naught is going to be negative 0.7996 volts. And we still have our AgCl plus the electron being Ag and Cl, with its E naught as a positive 0.22233 volts.
So negative 0.5773 or so.
Negative 57727, that is correct. Just once again pointing out that the one electron transfers in the oxidation, the other one in the reduction, and overall only one electron has been transferred. So at the end of the day, when we have our AgCl, oh, and we also canceled out our silvers. We have our AgCl breaking apart to be Ag plus and Cl minus. The E naught here is negative 0.57727 volts.
Is it always going to be like AgCl or like whatever compound breaking apart into the two ions?
Yes, and in fact, as we build more of these, and we're going to build some more of them, you always take whatever the solid is, you will pump an electron into it to break it apart, and then your other equation will see that metal doing its thing to balance out. So I'll do another one to show you, because the standard mercury electrode is another classic example of how this is done. Okay. What does this mean?
It's happening backwards.
It is not spontaneous, as written. It's going backward. Now, first of all, do I need to scroll up, guys, before I scroll down? Anybody need me to go back up real quick? Okay, so if it's going backwards, does this make sense? We expect it to, right? AgCl. Is it soluble or insoluble?
Soluble.
Because it's on the bottom in a pile.
We have solubility rules. Remember those old things there. Solubility rules say AgCl is insoluble, right? In order to get it in there in the first place, we had to pair it with nitrate because all nitrates are soluble. So we're asking silver chloride to break apart. And it's like, no. We're like, yes, break apart. And you're like, I don't want to. And you have 1 molar on my product side. Le Chatelier says, I'm going to shift backward until I'm at the concentrations I want to be. right? We loaded up the product side with 1 molar solutions when we know that AgCl does not want to be soluble. Le Chatelier, oh, hey, it's all coming back. Says it will shift left to reestablish equilibrium. So what does this do for us?
Creates an electrical current.
Oh yeah, but we're gonna get to the coolest part. This is where I like it. Okay. At 1 molar conditions. We are standard state. This means E is equal to E naught. But if E is equal to E naught and that log factor goes away, then that really comes down to this. The E naught is equal to 0.0591 over N log of KEQ. Because when we are at that standard conditions, E is equal to E naught, well then you pull the sorry, you pull the E naught over and you flip the sign on your log equation. But since we are at this thing, we can actually now calculate the equilibrium constant. Check it out. So the KEQ is the KSP, right? So what do we do here? We take N over 0.0591 times the E naught is equal to log of the KSP. If we tend to the on both sides to get rid of it.
Can you scroll back up after this?
Yeah, sure. How far?
That's fine.
Okay. So by doing it,
you can go down.
By doing it a standard state, we can make sure that E equals E naught. And when we're at that, we are going to actually change the Q to the KEQ, in our case, a KSP, because it's the solubility product. We'll go ahead and tend to the to get rid of the log portion. And so now we have 10 to the N over 0.0591 times E naught is equal to the KSP. Or their KSP is equal to 10. We had 1 electron being transferred over 0.0591 times the voltage, which was negative 0.57727. And if you do that, Dallas, what do you get?
Oh, I don't have my calculator with me right now.
Perfect. Ben, what do you get?
Still working.
Okay.
I got 1.7 times 10 to the negative 10.
I agree.
Bam. We started out equilibriums talking about the fact that the products over the reactants will equal some sort of constant. We went through some liquidy examples and then we did some solid examples. And one of our first solid examples we ever did was silver chloride breaking apart. And we listed that out as 1.8 times 10 to the minus 10. It should be no surprise that if we actually go to thermodynamic and electrochemical data, that at the end of the day, we should end up with exactly the same KSP. And we do. One of the ways you find out what the KSP of all these solids is to actually just design an electrochemical cell, measure the voltage, and back out what the solubility product is. It's easy. It's a whole lot easier than dumping a bunch of solid into a solution, waiting a couple hours, coming back, and then counting all the ions. It's a whole lot easier.
So what you're saying is that you would physically build this
Yes.
without already knowing / calculating the voltage, quickly measure the voltage, and then calculate the KSP?
Yes.
Okay.
So if you had some sort of solid and you're like, man, I wonder what it does. I wonder how soluble this thing really is, especially if it's really insoluble. What you want to do is you want to go through and you want to say, okay, how am I physically going to do this? Well, you can design an electrochemical cell for that self-same equation, and then basically as soon as you hook it up, take that immediate voltage measurement as everything tries to race toward equilibrium, and bam, you will have the voltage you can calculate this, the KSP from. It's actually pretty cool.
Also, a question regarding the Beardine.
Yes.
So you said that you'd put it in there, apply a positive voltage, and it would form the Beardine.
Yep.
That requires an outside battery source, right?
Yes, it does.
Okay.
So you go zap, you take off that battery, you go like, all right, now let's hook up the real thing.
All right.
Standard mercury electrode. This is another one that can be used. And I like showing you guys this one because it's interesting. What we do is we have Hg2, I2. And I want to break that into Hg2, 2+, plus 2 I minuses. This looks almost familiar. No, no one saw this.
Not recognizing it.
It was the first thing you had to do on the second exam. I just put chlorides instead of iodides. Okay, so what we're going to do first is we are going to.
Wait, are you sure it's Hg2 2 plus and 2
Yeah, actually-
I minus?
Actually, yeah, I'm pretty damn positive about that. All right, so what I'm going to do here is I'm going to take my Hg2 I2 and I'm going to pump in 2 electrons and I'm going to break it apart. I'm going to break it apart into 2 mercuries and 2 I minuses. That, of course, is the reduction side of me. On the oxidation side, I'm going to have 2 mercuries becoming an Hg2 2 plus 2 electrons. And actually, I'm going to go ahead and put the things over here. I'm going to say this is the reduction, the oxidation.
What is the E that's in parentheses?
Oh, it's not an E.
Oh.
L for liquid.
Oh.
So if you go there, you find that the E naught for this guy is negative 0.0405 volts. And the voltage for the oxidation one is negative 0.7973 volts. So at the end of the day, when you take these two together, Hg2I2 becoming the Hg2 2 plus 2 I minuses, since they've already been flipped around for you, the oxidation one has already been flipped around, so its sign is already there. The E naught there is negative 0.8378 volts. That is horrible handwriting there. 0.8378 volts. Okay. There should be no surprise, right? Mercury is also one of those things that doesn't like to play ball. If we wanted it to dissolve, we'd stick it with nitrate. We didn't. We stuck it with iodine and said, go for it. And it goes, no, you have 1 molar conditions on the right-hand side. We're going to go backward. And you're like, fine, do it. While you're doing that, we're going to measure your KSP. I want to go ahead and build this real quick, though, just because I think this is a cool one to see. Okay. So I'll just go ahead and arbitrarily put these guys here. On the oxidation side, we need, let's see, some mercury and some mercury 1. And on the reduction side, it looks like I need some mercury, some iodide, and some mercury iodide. Ben, you've been on fire today. Help me build this. What does it physically look like?
Step one, what are you going to do about the, because you have the metal on one side, which means you in theory be using that, but it's a liquid.
So use
I
it.
don't know how that works.
So use it.
You can
What would
still
happen,
use
Cal?
you
Go
can
ahead,
use
Ben.
HG on the left and the right.
Yes, you can. So where's that HG gonna go? I love this. Oops.
I don't know if it's going to be solid or in solution. Or not in solution, but just floating.
Kimchi, what is it? What's the physical state of mercury?
Solid.
Liquid.
Liquid?
Remember, you're the one that said, what's that E?
Oh, it's liquid. Well, if it's Hg2
Well, that's an ion floating around. That's different.
Okay, I got it.
So let's set the Wayback Machine for the many of you who took Chem 110 here. We had that lab where we said, take a look at these physical examples of your elements. And one of those was this little jar that was all paraffin waxed at the top and sealed up and floating around, and well, not floating, sinking around in a watery solution, was a nice little bubble of mercury just floating around as a little ball at the bottom of the jar.
Oh, mercury is liquid. Isn't that what's in thermometers?
Yeah, and didn't we just do that whole barometer thing where we said, oh, you weren't here, Kimchi. It was 13.6 times as dense as water.
Yeah.
Yep, and it just drops down to the bottom. This is what I love about this mercury, standard mercury electrode. So check it out. It's at the bottom. So how are we going to hook them up if we don't want any of the wiring to see the system? Like we can't just drop a copper. We can't just say, hey, let's drop a copper wire in here. We can't do that. We can't say, hey, copper, go, because copper will suddenly be in the solution here. That would be bad.
Make the base cuts out of the metal, wiring.
Put the wire on the bottom. Just stick it up through the butt. Right? Just go whoop, right up the back end there. It'll touch the mercury, but will not be part of the reaction here. So wire up from the bottom.
What about insulating the wire up until the tip in the bottom?
Yeah, that's, you kind of still don't want to do that. I mean, you could try, but it's when they make these, they actually basically just get the glass hot enough to shove the wiring up to just barely getting in there, and then just drop the mercury on top of it. That's just how it's done. And they usually don't just leave a bare wire, right? They'll build a base around it to protect it and things like that. So when you set it down, you don't just like crumple up the wire, but this is how they make it. I mean, technically, I guess if you filled it up enough, you could like come in from the side or something if you wanted. But yeah, it's kind of cool. It's kind of weird to think like, okay, you told me to use the metal, but this isn't a solid metal. It's a liquid. What does it do? Oh, well, it drops to the bottom. Well, then how am I supposed to touch it? Well, functional fixedness says we always come in from the top. You don't have to. You can come in from the side. You can come in from the bottom. As long as you keep that wire out of the solution, you are okay. So I always like that one because it's really, it's a clever thing that we don't always think about, and we wouldn't unless we had enough experience or we got lucky. All right. 1 molar Hg2 NO32. We're going to need that nitrate to get that in solution. On the other side, 1 molar potassium iodide, and we're just going to beard the Hg2I2.
Hey, what's the square thing between the
Oh,
cups?
that's the semi-permeable membrane. If you watch the last time's lecture, basically it allows for the ions to still flow, but kind of restricts it so they don't quote see each other. They eventually will, because things do move. We're just trying to slow it down so that one side doesn't see the other and do its reaction without our permission. Again, the electrons here, the electrons are going to be going this way. We have the anode and we have the cathode, which means our counter ion of like an I minus or something is probably trying to go back the other way. Now, keep in mind, I do want to point out that if our I minus is going through the semi-permeable membrane, it's not going to take it very long to see the mercury down there and start poisoning that mercury, right? And this is how your stuff eventually, dies, how it just doesn't work anymore.
So question. This thing is not spontaneous. If
As written,
anything I've been paying attention to makes sense. And so we're going to be saying that, in reality, it's going the opposite direction.
Yep.
But that would mean that the I minuses are going in the opposite direction and going from a place that doesn't have any to a place where it already exists.
No. Yeah, I guess maybe I don't understand that question.
Right,
what do you mean they're going somewhere they don't exist?
Sorry, I was muted. So the way we wrote this thing is that the I minuses are going from the right-hand side to the left-hand side, correct?
As the electrochemical cell starts working, yes.
Yeah, but given that the E naught thing we got was negative, that means that it's not spontaneous, correct? As written?
As written, which means that the Hg2I2 is not breaking up, but rather it is reforming. Now keep in mind, we have drawn this to do what it's doing here, what we want it to do. It won't do that. It's going to do everything basically the wrong way.
Yeah, so it's going to go backward. All this stuff is basically going to happen in the opposite direction, correct?
Yes.
So instead of the I minus going from the right to the left, it'll instead go from the left to the right?
No, actually, what's going to happen is the I minus from the Ki is going to start dropping out, and we'll see the electrons going to the left, which means the nitrates would have to be moving to the right in the actual circumstance.
Okay, thanks.
Yeah, now I understand your question. All right, so at the end of the day, we have negative 0.8378 for the volts is equal to 0.0591. And here we have 2 electrons being transferred, okay? This is where the N comes in. We have 2 electrons up there being transferred. And then log of the KSP. If you go ahead and solve it, you'll find the KSP is 4.50 times 10 to the negative 29. Pretty darn insoluble. I just heard a loud crash. Hold on. Everything okay? We just had a poltergeist decide that they didn't like the pictures of one of our trips and threw it off the wall. So sorry about that. Just want to make sure
Got n equals 2 from the number of electrons.
right. Okay. So now we built a whole bunch. Well, we built a few different cells here. We've balanced a few different reactions. What we need to do now, but before I go, is everyone okay with this situation, with what's gone on here? Any questions besides Dallas?
Is this what's in a Duracell?
Is this what is in a Duracell battery? No, I'd have to look up, and I really, every year I'm like, I should look that up. Dallas, while we're all chatting, why don't you look up the components inside of a Duracell battery? I forget the two metals. I think it is copper and zinc. I could be mistaken. So he'll look up what the two metals are.
And how toxic is zinc?
Not. Why? I mean, we take it all the time for a supplement if we're getting sick. We use it as electrochemical protections on ships. So just the act of moving through salt water for ships, because they are made out of iron, and iron will essentially steal from itself in order to satisfy its weird needs. They're floating through salt water, which acts as the electrolyte, and an iron from one part will steal electrons from another part, and then that iron will then combine with the water and give you rust. So what they'll do oftentimes, or at least in older times, and they still do it on smaller ships today, is they will actually put just chunks of zinc on the hulls of the ships. And as it's moving through, if iron wants to do something, zinc's like, I got you covered, and spits off its electrons, and it slowly dissolves off of the ship. And so when they come into port, they will have divers go under and see how well those chunks of zinc are holding up. One of my buddies had a sailboat, and he actually had a steel keel for the boat, and he would every so often just dive under, reattach that chunk of zinc so his keel didn't just rust away. Nowadays for the big ships, instead of doing that, because it'd be just prohibitive, they actually just run a very light current around the whole ship to counterbalance that and protect the hull of the ship that way. You can also do that with city waterworks. You know, a lot of cities still have old cast iron pipes that work. They're slowly, losing their integrity. So they found, okay, if we put some zinc here or there, or if we just run a constant current down it to basically counterbalance the water flowing through it, they can make them last basically indefinitely. Hey, Dallas, what Duracell has in it?
Yeah, Duracell claims that their batteries are composed primarily out of steel, zinc, and manganese.
Oh, manganese.
I assume
okay.
zinc and manganese are the electrical components.
I would say so as well. In fact, we'll talk a little bit about batteries if we get time today. What I want to do is how would this cell, this electrochemical cell, look on paper? And what I mean by this, in a book. Because you have to realize that once we figured out how to do electrochemical cells, we had to have a way of conveying this information to someone else, but it's only been a recent thing that we can actually print pictures. So they had to have a way of telling you how to build this cell without showing you.
The
And
same
so-
way we drew it.
Yes, very much. So what happens here is I'm just gonna basically use all of our examples. How this works is they say it like this: you start at the anode. Let me put this in a different color. So you start at the anode. Can I please write a little more legibly? Start at the anode. Swim through the solution to the cathode. Didn't think I'd have enough room, but I did. Tell me what you see. A little more scientifically, it is written as this: anode slash solids, gases, PPTs. I guess PPT and solid is the same, so let me just go ahead and say PPTs are gas. Slash any solutions that you see. The membrane. The other solutions that you might see. Any PPTs or gases that you're using. And then what is comprised of the cathode. Now I went ahead and color coded it as we've been color coding it, just to show you. And I think what I'm going to do, well, I'll ask you what you want to do, because I can either draw all of these electrochemical cells that we've been doing so far. Well, I'll do all the examples we've been doing, and I can draw them quickly, and then we can write this stuff out. Or I can just say, hey guys, look back at your notes, and this is how we're gonna do it. If I draw them, I will draw them quickly in such a way that I don't think you wanna try to catch up. So it'd be one of those that you would have to just sort of go back and watch this again. In a normal class, I would leave them all up on the board so that you could write them down afterward. Do you want me to just say, hey, remember that cell, or do you want me to draw it so you can see it?
You have the trouble of drawing it.
Okay. And again, if I'm going too fast for you to keep up with the drawings, just come back to the video for your notes. But what I want to do is look at all the examples that we have drawn so far and built so that we can see how we would write this in basically a paper. So quickly do. All of our examples. So our first one here was our zinc plus the copper ions. We're going to make zinc ions and copper. When we drew that, we had our zinc, and it was in, wait, was it zinc? On the left? Ooh, now I forgot. Well, it doesn't matter. Zinc with a 1 molar zinc sulfate. And we had our copper.
Zinc was on the left.
Thank you very much. 1 molar copper sulfate. Okay. Which one was the anode and which one was the cathode?
Anode's the zinc.
All right. So here was our anode. And there's our cathode. So what I want us to do is I want us to start on the anode, and I want us to swim our way through till we get to that cathode. This is going to be our path. Okay, we're going to swim our way through there. I'm going to go ahead and keep color coding it because I can. The first thing I see is zinc. Are there any solids or gases in the system?
No.
Nope. So then we go with our solution, which happens to be a 1 molar zinc sulfate. The next thing we see is the membrane. The next thing we see is a 1 molar copper 2 sulfate. And no solids or anything, so we just go to the electrode. This is what is called the cell diagram. Put that back up there. This is called a cell diagram. You guys with me? Except for Dallas. Alexia, tell me you're good.
I'm good.
Okay. Boudica?
Yeah.
Okay, lie to me. Sadia, I know I normally don't call on you, but I just want to hear a different voice. Tell me you're good.
I'm good.
Okay.
What is the PPT mean? I didn't hear that.
Oh, PPT is shorthand for precipitate, solid.
Okay, cool.
Yeah. Okay, our next one, we had the iron 2 plus the silver plus. Going to make Fe3 plus and solid silver. We drew that cell. And did we put the silver on the left or the right? I think this is the one I went backward on purpose for you guys.
Left.
I put the silver on the left? All right. So I put the silver on the left and I put the iron on the right. So on this side, I'm just going to go ahead and choose platinum. On the silver side, I had silver. And the silver was 1 molar AgNO3. And on the platinum side, I had 1 molar FeCl2 and 1 molar FeCl3. In this circumstance, I had the anode was on the right and the cathode was on the left. I know in all the rest of the ones we did, I once again fell victim to the subconscious of writing it anode to cathode, left to right. And I would actually almost encourage you guys to get into that mantra. But if you happen to have done it this way, as long as you have it labeled right, you're okay. So again, we're going to go from the platinum to the silver, going from the anode to the cathode. So we start with our electrode. That anode is platinum. The next thing we'd see, are there any solids or gases? No, so we have, looks like two solutions going on here. And that is, we have 1 molar FeCl2 and 1 molar FeCl3. The next thing we have are the slashes for the membrane. The next thing we see is 1 molar AgNO3. And the next thing we see is the silver. And that basically tells you, okay, if I read this, I know what my pieces are, I know what side they should be on, or you know, not that the side matters, but I know all the things that I'll need to put on there in order to make it work. If you have more than one solution, go with your bad self. That's okay. Just list them all out. You guys ready to see the next one? Or somebody frantically trying to write this down too? Or are y'all just sort of watching? Ethan, so you normally write stuff down. Are you cranking along, or are you just watching?
Oh, I've been done for a while.
Oh, damn.
I've been able to write it too.
Yeah.
Oh, good, man. Okay. So you're like, oh, well, hurry up. Okay, fine. I'll go faster. All right, so we had this one. So let's see, the standard hydrogen electrode. Let's see if I can remember how I did this one. I went ahead and made a little bubbler. I made my salt bridge to my other cup. And I had my zinc electrode in there. I had my 1 atmosphere of hydrogen, and I had my platinum mesh in here. And I had my 1 molar HCl. And on the zinc side, I think I had 1 molar zinc sulfate. All right, so since this was that H plus 2 electrons going to H2, that meant that this was the reduction, which meant it was the cathode. And here we had the zinc becoming zinc 2 pluses plus 2 electrons, and that was the anode. So we'll start from the anode and start swimming. So the cell diagram would look like zinc, 1 molar zinc sulfate. We got our salt bridge, which is our membrane. And then what's the next thing we see? We see the solution, 1 molar HCl, and then we see 1 atmospheres of hydrogen, and then the platinum. There's where your precipitate or gases come into play. Oh, then we had this nice little cluster, didn't we? We had the, now let me look up the equation for it again. It was our, whoa. Then we had our I minus plus CR207. I believe that's the one we're doing right now. Yep. Going to make the iodate plus chromium 3 plus. In each of those, let's see.
Platinum or carbon.
Right, so I'm just gonna go with platinum just because. We had platinum for both of these. And yeah, it's okay if you put carbon. I'm just doing platinum because. And then I think we said we had
Ki, KiO3, and HCl. On the other side, K2CR3O7, CrCl3, and HCl.
okay. So we built this one. And now we just do the cell diagram. Ooh, that's a lot of writing. And again, just to remind ourselves, we're going to start here. And we're going to swim our way over from the anode to the cathode. So we start out by seeing the platinum. And then 1 molar Ki, 1 molar KiO3, and 1 molar HCl. Ooh. I wonder if I can just, well, no, can I undo that? There we go. I'm gonna have to do this on 2 levels here. So we see the membrane, then we see the next solutions of 1 molar K2CR2O7, 1 molar CrCl3, 1 molar HCl, and then finally platinum again. Silver chloride electrode was our next one. We had silver on both sides. And inside we had 1 molar AgNO3. We had 1 molar HCl. And we had our AgCl bearding. Still keeping up, Isa? Low band?
Yeah, I'm good.
Yeah, I'm good.
These are flying. Are you doing colors too?
Yeah.
Yeah.
Man, rock stars. All right, well then, Isa, tell
Yeah.
me, how am I gonna write this cell diagram?
You're gonna do your silver,
Okay,
and then you're gonna do 1 mole of silver nitrate,
1 molar silver nitrate.
and then you do your what is it? The membrane thing,
Yep.
and then you do 1 molar of HCl,
Hmm.
and then you do your silver again.
You forgot the precipitate, right? We have to swim through all this, and we got to swim through that AgCl.
Okay.
So you have to put that before you get to the electrode. And I'll answer your question now, Dallas. Had you put that lump on the bottom, you would still see that precipitate before you saw the electrode. Don't ask me why, magic. But this is how you draw it out. All right. Standard mercury electrode. Drew that one. Here we had our solid mercury on the bottoms. And we had 1 molar Ki. And we had 1 molar Hg2, NO32. Anode to cathode. Low band, you're up.
Okay, so start with Hg.
Okay.
And then you're going to go to 1 molar solution, Hg2, nitrate 2.
Okay.
And then double lines go to 1 molar Ki. Another slash Hg2Cl2 slash Hg.
Nice. Is everyone else just like running with this?
Pretty much.
Good. That's what I like to hear. I have 2 pages left, guys. That's it.
Hey, was it Hg2Cl2 or Hg2I2?
Sorry, I2. Sorry. I went back to your exam too. Sorry about that. I think I am going to finish this out. This will answer Ben's question from the beginning of this. And it's just 2 examples of batteries. Oh, 3 pages, and then a fuel cell. And then we'll discuss whether or not and how we want to do the next exam. Unless you guys have thought about it, do you want to have the exam on Tuesday or on Thursday?
Thursday.
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 Oh. Okay.
I
Well,
have
if you,
another final on Tuesday.
all right. Well, if you guys want to do it Thursday, then I will actually save the batteries for next Tuesday then.
Yay.
They won't take us very long. And they're just to show you the practical applications of batteries in general and how these electrochemical cells work. So maybe we'll just call it a day here, and we'll finish it up Tuesday. And we'll still have time, plenty of time for other questions about exam 3. Now, the thing is, you guys will take it Thursday. I will try my best to get it graded as fast as possible. And I will try actually to see if I can't just get them done that day, so that on Friday, you guys can take a look at what you missed or something, so that we can fill in those gaps before the final comes.
So exam 3 next Thursday and the final the following Tuesday or the following Thursday?
Yeah, the following Tuesday. Well, let me think about the date of the final. Does everyone want it on Tuesday?
No.
No?
Can we do it a week later on Thursday?
Yeah.
You mean
I don't want finals back to back.
instead of Tuesday the what?
Thursday the 26th, Thursday the 28th.
Let me get a calendar real quick. Wait for it. So you're saying instead of Tuesday 26th, Thursday 28.
Yeah.
Yeah.
Correct.
Okay. What I'm going to have to do, actually, guys, is I'm going to have to send that out in an announcement, because I still don't know how the online thing works. I don't know if I have to hold my final on that day. Let me double check, but I am open to making it that Thursday. Let me just make sure I can, and I'll let you guys know. In fact, I'll let you guys know by the end of the day if we can push the final by a couple days.
Thank you.
I'm happy to do that for you guys.
Thank you.
Not a problem. All right, I'm going to go ahead and stop the recording here.